We're going to talk about another really important topic here, continuity and discontinuity of a function. Our objective this time is to determine continuity at a point and on an interval. Now, what I want you to think about graphically, what continuity means graphically. A function is continuous. Let's think of it as continuously drawing the function if we're graphing it. So I'm going to just put in parentheses because this is not a definition of continuity, but we want to think of it as can draw the function without picking up our pencil. Meaning you don't have to pause because there's a hole. You don't have to pause because there's an asymptote, but it's just a continuous smooth curve or line or whatever. There are no holes when it's a continuous function. So what does that mean if there are no holes? Three things have to happen, and these are really important, must be memorized. First of all, the function value everywhere has to be defined. There cannot be any holes. F of C must be defined, no holes. Now what I'm putting in parentheses is a way you can think about it. What I'm writing here is exactly what needs to be memorized. The function value is defined, no holes. Also, the limit as x approaches any value of the function has to exist. So there may not be any jumps, okay? No jumps. Now, keep in mind what we talked about last time with one-sided limits is what that means for the limit to exist is that the limit as x approaches that x value from the left has to be exactly the same as the limit that x approaches the value from the right for that function. So no jumps, no holes, no jumps. So the function value defined, the limit's defined. Then it has to be true that the limit has to equal the function value. So we've always said that the limit means where's the function headed. It doesn't actually have to get there. Well, for a continuous function, yes, it does. The function has to get there. So the limit equals the y value, which means the function must get where it's going, has to reach that point. If a function is continuous on an open interval, that's going to look like this. So on an open interval, so there can be holes at the endpoints like this. Call that endpoint A, endpoint B. That's continuous on an open interval. Continuous on a closed interval, this notation, open interval, this notation, those endpoints have to be closed dots and then continuous everywhere in between. So I just want you to think about what that means graphically. Then we've got two types of discontinuity. One type is called removable because it can be easily fixed. That's a hole. And when we think about how that looks in the function, it can factor out, and we'll look at some of those. The other kind of discontinuity is called non-removable because it cannot be simply fixed. Those are asymptotes and jumps. And if we see them in the expression of the function, those are not factorable. Let's take a look at a couple of examples how to use this definition of continuity. So again, we have this picture from the other page. Use the graph of g of x to answer the following. Here's our graph of g of x. For what values of x is g of x discontinuous? So if we just think about it as can we draw it without picking up our pencil? If I start over here, I'm drawing, and uh-oh, there's a jump. I have to pick up my pencil to continue drawing the function. So this is the first location of a discontinuity. 1, 2, 3, 4, -4. So we're going to write x equals -4. That's the value of x. That's what they asked for, the value of x. And it says explain why by using one of the three parts of the definition of continuity. Again, really important to memorize that definition. So the part that we're talking about is that since there's a jump, the limit from the left doesn't equal the limit from the right. So from the left, from the right, those are different. Therefore, the limit doesn't exist. So I'm going to say at this point, because the limit as x approaches -4 for g of x does not exist. Now let's keep drawing, 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 drawing. I don't have to pick up my pencil until I get to this hole. I have to pick up my pencil to jump over it and keep going. So there's a hole right there. And that's at 1, 2, 3. That's at x equals 3. So there's the other location. And this time, coming from the left and coming from the right, it's the same, but what's happening here is there's a hole right there. So at that point, there's a hole. So that means the function at 3 is not defined. Oops, and I accidentally wrote f. I know you guys didn't, because you are quicker and more careful than I am, because the function value at 3 does not exist. Now, what types of discontinuity are these? Well, remember that when it's a jump, like at x equals -4, those are harder to fix. So those are non-removable. Oops. And if I can simply just fill it in by coloring in that little hole, like at x equals 3, that one is removable. And then it says for what values of x is g of x continuous? What values of x? And I want you to practice using intervals. So what we're going to say is, assuming that this graph continues this way and this way, we're going to start our interval at -infinity. And we're going to say that I can draw it all the way up to -4 and it's filled in there. So I'm going to say -4 and put a hard bracket. Union, now when I jump up to the next part, there's a hole there. So that has to be a soft bracket at -4 because I can't color in that spot. Go, 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 go until I get to 3. There's a hole there. So at 3, we're going to have a soft bracket on both sides, continuing from 3 to infinity. Let's look at a problem that doesn't have a picture for us. So here we see, ooh, AP problem, very important. We want to feel comfortable with these. We might see them on a quiz or test, and on the AP test, most importantly. If the function f is continuous, and if f of x equals this expression when x doesn't equal -2, what does f of -2 have to equal? Well, here's my keyword, continuous. So immediately, I want to think of the definition of continuity. 1, f of, now I'm looking at that value of -2 when x doesn't equal -2. I see here that if I say x plus 2 equals 0, because there's a denominator, I get x equals -2. That's going to make my denominator 0, so that's a point of most likely discontinuity. So we want the function value at -2 to be defined. So thinking of our definition of continuity, f of -2 must be defined. That has to happen. Second, the limit as x approaches -2 for our function has to exist. And thirdly, these two guys have to connect. The limit as x approaches -2 for our function must equal f of -2. So those are the three cases that we're going to look at. So let's observe this function. First, number 1, f of -2. What is it? Well, that's the question they're asking us for. So I don't know that yet. Second, the limit as x approaches -2 for our function, so our function is x squared minus 4 over x plus 2. I can't use direct substitution, but I can factor. So let's rewrite this as the limit as x approaches -2 of x plus 2 times x minus 2 over x plus 2. X plus 2 factors out. With what I'm left, I can do direct substitution, plug in the -2 minus 2, I get -4. Lastly, we know from our definition that the limit as x approaches -2 for our function must equal the function value at -2. Therefore, since we know that the limit as x approaches -2 for our function equals -4, then f of -2 has to equal -4. We've answered our question.